Alright, so I want to tell you about a new feature that's coming out in Sage version 9. Sage version 9. That's probably going to be out in probably January of 2020. It's December of 2019 right now. It's in beta release. I'm going to show you like a beta release version of the code. But it's a multivariate factorization over the algebraic field. So let's look at some simple polynomials. Let's look at this one. Let's look at x, not that one, x squared minus 1. And this factors as x plus 1, x minus 1, fairly simply. If we look at x squared minus 2, this would factor as x plus the square root of 2, x minus the square root of 2, as you can easily confirm with like FOIL. But of course, to factor this one, we need to introduce this the square root of 2, and then the question is just do we allow that? Do we allow square roots into the mix? And really, the answer is that factorization depends on what the coefficient field of the polynomial is. So some rings factor these polynomials, and some of them do not. So let's just make a list. Do not factor, right? Factor and do not factor. So this one factors in the rationals, rational rank extended by x, reals, quite what I wanted to do there, reals, and complex numbers. But this one only factors in the reals and the complex numbers, at least of these three possibilities. It does not factor over the rational numbers q. If you just did q, square root of 2 is not in q, so this polynomial is irreducible. And then if we throw in something like x squared plus 2, well, now we see that, of course, we need our old friend I to factor that. This one of these possibilities only factors over C and does not factor over either the rationals or the reals. So depending on what field we choose for our coefficient field, we get different factorizations, different polynomials, irreducible or reducible factor can be factored or not factored depending on what our coefficient field is. Now, of these possibilities, you might want to look at this and think, well, it looks like this one, C, the complex numbers, this is going to be our best choice if we want to factor everything. But there's a bit of a problem with C on a computer algebra system, and that is simply it's too big. It can't be easily, really, it can't be represented. You can't represent an arbitrary complex number in a computer algebra system. You can do an approximation. You just look at the real number, reals and complex numbers. You can do an approximation, but you can't exactly represent a complex number. So if we want to do this kind of a calculation, it'd be nice if we want to, we would like to have an algebraically closed field, but one that is also computable, and what C is not. And the primary candidate we're interested in is Q bar, which is the algebraic field, and that is the algebraic closure of Q. It's Q plus all roots of polynomials, so all of these things factor over Q bar. We would add Q bar to the list of the rings here where all three of these polynomials factor, and it has the advantage that it's representable in the computer. It can be slow. Doing calculations in Q bar can be slow. Now, all of this, and if you switch to Q bar, Sage for a while has had an implementation of the algebraic field, and you can use it with, I'll show you how to use it with QQ bar. All this has been done so far in Sage. What has not been done, what is new in Sage 9 is this. Let's say I wanted to do this kind of factorization. I want to now do a multivariate factorization of a polynomial, factorization of a multivariate polynomial. So I expect that I'm going to be able to do something like this. But in fact, Sage couldn't do this prior to version 9. Just it could not factor. It could do this over like Q. It could do this over a number field which you set up ahead of time to have square root of 2 in it, but it couldn't just automatically do this extension and do this calculation over the algebraic field Q bar, which is what we're interested in. We're interested in multivariate factorization. So let's just start by taking a quick look at how we do this in Sage. Let's just start this is a beta release of 9.0. It's it's just what is it, December 8th. It's 9.0 is coming. This is a pre-release of 9.0. So let's say how we want to set this up. And you say r xy equals. We could do QQ and then take something like, what was it, x squared plus 2, I think I had 2y squared, right? And factor it. And of course it doesn't factor because we need these things. We need these, I square root of 2. We need things that aren't in Q. So how can we get that? Try and use something like this, which is going to be the complex, but this is only an approximation. CC is only a complex field with 53 bits of precision. This is a floating point approximation, and this doesn't work. We get an error on this because we just don't have good factorization in an approximate field. What we can do though is use QQ bar, which is our algebraic field. And now when we do this, we get a factorization. QQ bar by default shows a decimal approximation, but this is not a floating point number. Internally, this is stored exactly. You can tell it's a little bit different because of this question mark here at the end. The question mark at the end is the way Sage indicates that it is actually an exact number, and an exact algebraic number, and not a floating point approximation. We can do this. We can set QQ bar options display format to be radical, and then if it is able to, it will display it. All we really changed was the display format. This is not the default because it can be slow. This can really slow things down. It will compute a radical form if it can find one, and it might take it a while to do that for complex, but that's no pun intended there. For a difficult calculation, this could be very time consuming, so it's not the default. You have to set that to be the default, and then you get something like this. This calculation did not work prior to version 9. Let's see. So let's take a look here. This is some of this is the source code that implements it. I'll show you in a minute how it a little bit about how it works. But here's an intro. Here's a test case from Singular. This shows a kind of a complicated polynomial here, P. This is a x and y. It's a multivariate polynomial, so we factor this. We will, and it chugs along for a while, and we get this factorization here. We can look at it in a little bit nicer format if we put it in a Jupyter notebook. So I'll start Sage with a -n switch, so it puts it into notebook mode. Here to the web browser, and here it goes. So we'll go to the Jupyter Notebook. We'll ask for a new Sage session. And what will we do here? Let's do again rxy equals qq bar. So again, this gives us a multivariate ring over qq bar, and there is the cut buffer, the polynomial p. And now I'm going to say display LaTeX, set my display format to LaTeX, and I also have, well, and just take a quick look and see what happens here. It's not going to display quite the way I want it. It's going to give us the numerical approximation here. We get all this stuff. But now, once again, I can do QQ. This is a new session. Didn't remember the options. Display format equals radical. And now factor again. And there we go. Now we get a nice, nicely formatted, LaTeX formatted radical factorization of this multivariate polynomial. Could probably be cleaned up a little bit here. You can see this this thing, this 1 over the square root of 5. You could bring the square root of 5 out of the denominator into the numerator, and if you were to bring it out here and here, to do that, we have to multiply each one by the square root of 5. So we have to multiply it by 5, and you will see these are cubes. So in fact, and there's a 5 cubed right there. So we could clean this up a little bit by just moving the 6 square roots of 5 into these two terms here. And then we would get, what would we get? We would get something like the square root of 5x minus y cubed, and square root of 5x plus iy cubed, and then the rest of it here, and x minus y to the fourth, and so on. Do the rest of this expression. Anyway, coming in just briefly, how is this implemented? This is the code where it's implemented, and this is this is the basic idea that I got from a textbook by Getty's. Did I cite that somewhere here? An algorithm. Yes. I don't know if I mentioned it. Probably in this PDF I talk about where I got the idea from a textbook by Getty's, and some of his co-authors that I read years ago that gave a very nice way of doing factoring, because we don't just have to factor, like, I mean, the example I used was what, x squared plus 2y squared, but we also want, I mean, how do we do something like this? This one we'd have to expand out to be now x minus the fourth root of 2iy, and x plus the fourth root of 2iy. This polynomial is in the algebraic field, the xy ring over qq bar. So how do we factor something like this? This is the probably the most challenging. Just factoring this one isn't. Well, polynomial factorization is not trivial, but we factor this by using singular. Singular has absolute, what it calls absolute factorization, and we just use singular as a subprogram under Sage. So singular can just factor anything in a ring like this, or this, or any finite number of indeterminates. It can factor over Q. That is, it's an algorithm for absolute factorization. Then the question is, how do we extend that to do something like this? And this is the trick from the Getty's book, and that is that if we have something like this, we can compute the norm, the field norm of F would be, this is an extension field, so we're looking at Q extended in this case to a number field, a number field generated by the square root of 2. So basically Q plus the square root of 2 and coefficients, so everything of this form, this is in this number field. And then we use the norm, which is the product of all of the conjugates of F. So it's a product over theta, or sigma in this case, where sigma are all the automorphisms of the number field here that fix the base field. So in this case, it's there's two of them, because the square root of 2, I should say, alpha, where alpha squared equals 2. This embeds in two different ways into Q. It has, or embeds in two different ways into C, into the complex, or R, either one, the complex numbers. It embeds once where alpha goes to the positive square root of 2, and then it embeds another way where alpha goes to the negative square root of 2. And then the automorphism we're interested in is the automorphism that just swaps. Alpha goes to negative alpha and everything else stays the same. And the norm is defined as the product over all these conjugates. So in this case, it would be the norm. I'll just go to another screen here. Let's take x squared plus the square root of 2y squared, and we want the norm of this, and the norm is always relative to some extension. So the extension here is q to this number field. This norm is going to be this. It's going to be this. This, I mean, it's the product over the sigmas. And the first sigma is always just the identity. And because this is a second degree field, the other sigma is just the automorphism that flips the sign here. So we get this. And then if we want, there's just difference of squares, right? So this thing becomes this. And notice the square root of 2 vanished. This is a property. This is the key property of norm that Getty's showed how to exploit, and that is that by applying the norm, you always get back to the resulting polynomial. When you multiply all these the automorphisms of all these functions together, you get something that is back in the original field, which is what we want, because now we can use singular to factor over Q, whereas we couldn't use singular. It just doesn't implement anything to factor over a number field, but it can do the factorization over Q. So we can factor this. And not only that, because of the way norm is defined, it's defined as a product. Well, it's not that hard to see that this is this is sigma applied to F. Just like this. But because of the way it's defined, it commutes with multiplication. So, and we just here, just a bunch of things multiplied together. So because it commutes with multiplication, we're looking at factorization, say f1 times f2. It could be as many of these as we want. It's sigma f1, f2. Well, sigma also commutes, it's an automorphism, so it field automorphism. So this commutes, and what we actually get here is a bunch of factors. So now we can factor this polynomial over Q, and then we want to intersect it with just this one, essentially. We can get a factorization over Q of this one. We can extend into this number field, and basically then the greatest common, you see if this one factors and this one factors, the f is the original factor here. So when this thing factors, it's going to give us, it's going to factor completely, because that's what the singular algorithm does for us. It's going to give us 2 factors from here, and it's going to give us 2 factors from here. So this is going to give us 4 factors. We could just look at, let me see what they are. I mean, I can almost tell you what they are, but let's just say it's, it's x to the 4th, what was it? X to the 4th minus 2 times y to the 4th factor. There they are. There are 4 factors, and now we just need to find which of these 4 factors are also factors of this, or it's going to be these 2, the ones that are also factors of the original polynomial. That would discard these extra norm product terms, and really to do that, it's basically just a GCD calculation. The way it's actually done is, once the code has computed this factorization, then it goes and just checks each factor to see if it divides the original polynomial. In this case, let's see. Oops, not the one I wanted to do. In this case would be, what was it, x squared minus, what was it, plus? We did plus, yeah. Plus square root of 2. It might be a little bit of trouble. Let's see how this works. I think this square root of 2 might not quite work well. Let's just see what happens. Yeah, that one didn't work too well, because that is not a QQ bar factor of 2. Let's make sure we put square root 2 in QQ bar. You think, why should we need to do that? And I would agree with you, that does seem a bit needless. That, but yeah, if you, this, what do I do here? I don't want that. I want this past QQ bar. This is already in QQ bar. The problem is this square root of 2 is, it's what is it? It's going to be in Sage's symbolic ring, which is kind of a loose and fast. It's good for like doing a lot of generic calculations, but it's not the square root of 2 we want. We want a square root of 2 in QQ bar. And if we do this now it factors. Now we get the 4th root of 2 and the 4th root, the 4th root of 2i and negative I that we expected out of it. And how it did this is it just computed the norm, got this thing, and then just did a calculation of each of these factors and said, well, do they divide this polynomial we were trying to factor? And of course identified that this one and this one and this one both factored, and they come down to here and here, and then these 2 were the extraneous ones that were introduced by the norm calculation, and they ultimately just get discarded. The norm calculation is, interestingly enough, done using a resultant. The resultant, which is basically, it's a determinant. You just take the 2 polynomials, which in this case are the polynomial we're trying to factor and the minimal polynomial that generates the number field, and we set up this Slater matrix, the Sylvester matrix, and we set up this determinant, calculate the determinant, and has an interesting property. It's very useful for us here. See this? See the lambdas here are the roots counted by their multiplicities of a, and the mu's are the roots of b. Notice these 2, like especially this one. Just look at this one here. The resultant is the product of the b polynomial evaluated at all the roots of a, and it's also the a polynomial evaluated at all the roots of b, with some extra coefficients tossed in the front. But it's basically you're evaluating the, you get these two polynomials, and just a matrix calculation of their coefficients, you can evaluate the one polynomial at the roots of the other. Well, that's exactly what we're trying to do with a with this norm calculation. We're trying to evaluate f in this case at all the roots of alpha squared equals 2, which is the defining polynomial here, and there are two roots, right? There's square root of 2 and the negative square root of 2. Well, here it is evaluated, now we'll call this alpha, x squared plus alpha y squared. This is the minimal polynomial. So what we're doing is we're taking the resultant of this polynomial here, alpha squared minus 2, and then this one too, x squared plus alpha y squared. This is the calculation we're doing. We're doing this resultant calculation, and what that gives us is this whole thing here. It gives us, in this case, this polynomial evaluated at all the roots of this polynomial, which is exactly what we're trying to calculate here. And all that's needed is just some linear algebra. Just take these coefficients, 1, negative 2, x squared, y squared. They're considered coefficients here because we're looking at it as we're looking at it basically as q, x, y, and probably even as a field. Probably, this is how we're looking. The resultant is constructed with respect to it is of a single variable. Take another look at it here. So we take we have two polynomials and a single variable. We pull out their coefficients and we form them into a matrix. That's the Sylvester matrix. The coefficients just have to come from some field, and in this case, this is the field we use. And then, what we're interested in, these are, it's then this one with the roots of this one plugged into it, and that's how we do the calculation. That's how we get our multivariate factorization. So we can now do these kinds of these kinds of factorizations, these kinds of factorizations. This thing that we did here, where did it go? Here, yeah, this thing here, factoring, and it works with more than two variables. You can do this with multivariate rings of any number of variables you want, and you get these kinds of factorizations of the algebraic field. If you're doing it with just a univariate polynomial, it is in a sense trivial, because q bar, the algebraic field, because it's algebraically closed, of course, a univariate polynomial will always factor down to linear terms. But that's not the case in the multivariate case. You see what we got in the multivariate case? We have some essentially linear terms here, but not all of them. This one here, this is a single irreducible nonlinear term, and that is to be expected because even though the coefficient field is algebraically closed, and that means univariate polynomials factor all the way down to linear terms. That is not the case on multivariate polynomials. So that's just a nice new feature that we got in upcoming release of Sage 9.